Hello students. So in many practical applications, even in the case of the industrial applications, the value of the function, so the extreme value of the function, either it can be maximum or minimum, plays a very important role. For example, if you want to maximize the profit of a company, if you want to find the highest temperature on a particular surface, so all these they all play a very important role in the practical applications. So in today's class, we are going to learn about how to find these extreme values of the function of two variables. So let us consider a function which is going to depend on two variables x and y. So today we are going to learn the procedure to find the maximum, otherwise the minimum, or sometimes there might not be maximum or minimum as well. So all such scenarios we are going to study today. So before we start the process or the procedure for finding the extreme values, so let us have some hint of the notations that we are going to use. So the given function, let us call it as f of x comma y. So the partial derivatives are required to find the in the procedure of finding the maximum and minimum. So let us find first the derivative with respect to x, that is dou f by dou x, dou f by dou x. So in shorthand notation, we'll denote it using just fx. Similarly, the next notation is dou f by dou y, next derivative is dou f by dou y, so which can be represented using the shorthand notation fy. So these are the first order partial derivatives that we need. Also, some of the second order partial derivatives are required. They play a very important role in the procedure. So if we go to the next second order, the first second order partial derivative, it is a second order derivative of f with respect to x itself. So which we are going to call it by the notation r. Okay, so otherwise in the shorthand notation, we already know that it can be written as fxx. For our procedure, we are going to call it as r, small r. Next, the mixed partial derivative dou square f by dou x dou y. We will call it as s. Okay, in shorthand notation, it is fxy or yx based on the variable which we are going to consider first. And the last one is dou square f by dou y square. It's the derivative with respect to y 2 times. We'll call it as t. Okay, otherwise fyy. So these are the partial derivatives that we need, and these are the simple notations that we are going to use. So looking at the procedure, the necessary condition for a function to have maximum or minimum at a given point is that the derivative of the function, the partial derivative of the function with respect to x at the point a comma b, the point which we are going to consider, should be equal to 0. Also, the derivative of the function with respect to the other variable y at the same point a comma b, that also should be equal to 0. So these are the set of necessary conditions that are to be satisfied by the given function to have the extremum value at the point a comma b. So similarly, now let's say we have the point a comma b, and how do we get to know whether it's going to be a maximum point or the minimum point? So that's what we are going to do. That's what we are going to see right now, and that comes under the category of sufficient conditions. So the sufficient condition is that we have already seen the notations already. The second order derivatives that's what we are going to use to define the sufficient conditions. So what we are going to do is we are going to evaluate the partial derivatives r s t at every critical point, and we are going to find something called as rt minus s square. If this quantity rt minus s square is greater than 0, then we have the two possibilities. One possibility is when r is also if rt minus s square is greater than 0, and if r is also greater than 0, then we say that the point is the point of minimum. And if rt minus s square still stays positive, rt minus s square is greater than 0, but r is less than 0, then this will be the point of maximum. That will be the point of maximum. So what if rt minus s square is going to become negative? If rt minus s square is going to become negative, then the point is a point of neither maximum nor minimum. In such cases, the points will be called as saddle points. So if rt minus s square is becoming less than 0, we do not worry about the r value. So directly you can just conclude that it's a point of neither maximum nor minimum. Otherwise, it is also called as a saddle point. So next, the last category is, the last case is, what if rt minus s square is equal to 0? So if RT minus S square is equal to 0, we are not in the position to conclude whether the point is of maximum, minimum or the saddle point. So in fact, that requires further investigation. So we will just say that the case is doubtful and it requires further investigation. Because whatever the derivatives that we are using, we are just using only up to second order partial derivatives. So for the fourth case, we may need the third order partial derivatives that we are not going to cover here. So now let us just have a very simple example right now to demonstrate this particular procedure. So the procedure is that first what we are going to do is, first step, we will be finding the derivatives. We will find fx and fy and we will equate them to 0. So that will be our first step. So when we equate fx and fy to 0, we will be able to solve these two equations, fx equal to 0 and fy equal to 0, and we'll be able to find the points called as stationary points, otherwise called as critical points. So once the critical points are ready, next we should be moving ahead with the process of finding R, S and T. R, S and T. So you find the second order partial derivatives first, R, S and T. So once R, S, T are ready, you substitute the critical points into the expressions of R, S and T. So you evaluate R, S and T at every critical point, and based on the conclusion, based on the conditions that we saw, if RT minus S square is less than or greater than 0, we can have the conclusion as well. So let's pick up a very simple example right now. So let us consider f of x comma y to be x cube plus 3x square plus 4xy plus y square. So let's consider a very simple example. So as I told you at the beginning, the first step is going to be, you're going to partially differentiate f with respect to x, also with respect to y. Okay. So the partial derivative f with respect to x is going to give us 3x square plus 6x plus 4y. So we are differentiating with respect to x, keeping y as constant. Next, with respect to y, if I differentiate, first two terms are going to give me 0, and the third term is going to give us 4x plus 2y. Okay. So what we need to do in the next step, we are just going to equate these two equations to 0, the two partial derivatives to 0. So we can call the first one as equation 1 and the second one as equation 2. Okay. So we must remember that the critical points that we are going to get, it will be the result of both of these conditions. So if you're getting the x and y values from one of these conditions, we are not supposed to pair them up. So if x is from one condition, y is from the other condition, only then we should be able to pair them. Only that's going to be a valid critical point. So to do that, what we are going to do is, from the second equation, so we know that we have 4x plus 2y is equal to 0. From this, we can find that y is going to be minus 2x. So y is going to be minus 2x. We'll substitute this y is equal to minus 2x in first equation, and we'll be able to find the critical points. So substituting in equation 1, so you get 3x square plus 6x plus 4 into minus 2x is equal to 0. So when I simplify this further, I'll get 3x square minus 2x is equal to 0. So we have 3x square minus 2x is equal to 0. Taking x common, we get 3x square minus 2 is equal to 0. So 1 minute, sorry. This is just going to be 3x minus 2 is equal to 0. So we get either x equal to 0 or x equal to 2 by 3. Okay. So we got two values of x. So this we can substitute in the recent condition that we had. You can just see that here. Y is equal to minus 2x we had. So in this, if I plug in the values of x that we got right now, we'll be getting the two critical points. So y is equal to minus 2x. So if x is 0, the first value of x if I take, y will also be 0. If x is 2 by 3, then the value of y is going to be minus 4 by 3. So basically the first one is going to give me the first critical point 0, 0, and the second one is going to give me the second critical point 2 by 3 comma minus 4 by 3. So now let us quickly look into how these critical points are going to play the important role in deciding the extrema. So are they going to be the maximum point, minimum point, or the saddle point? So let us go to the second order partial derivatives. R is fxx. Okay, so which is nothing but the derivative of fx with respect to x again. So we know that our fx was nothing but our fx was 3x square plus 6x plus 4y. If I differentiate it again with respect to x, I'm going to get 6x plus 6, 6x plus 6, this is r. S is going to give us, let's go back to fx. So if I differentiate fx with respect to y, I'm going to get fxy, which is our s. So first two terms are going to be constants, yielding you 0. The only 4 is going to remain. S is 4 and t is derivative of fy with respect to y again. So which is going to give you 2. So now based on the, now let us just quickly substitute the points. So let's consider the first point 0, 0. The first point is 0, 0. So r was 6x plus 6, which is going to give us 6 at the point. S and t are not going to change. S was 4 and t was equal to 2. So rt minus s square, r into t is 12 minus s square is 16, which is going to give us minus 4, which is less than 0. So we know that when rt minus s square is less than 0, we say that the given point is a point of neither maximum nor minimum. So therefore, 0, 0 is a saddle point. It's a point of neither maximum nor minimum. Now let's quickly look into the next point. Case 2. Case 2, the point is, the previous point was 2 by 3 comma minus 4 by 3. So let's find RST. R was 6x, 6 into 2 by 3, 6x plus 6, which is equal to 3 2s are 4 plus 6 is 10. S and T are not going to change. S is 4, T is 2. So RT minus S square is going to be R into T is 20 minus S square is 16, which is 4, which is greater than 0. So R was also greater than 0, as we can see, and RT minus S square is also greater than 0. Since both of them are greater than 0, we can conclude that the given point, the 2 by 3 comma minus 4 by 3, is a point of minimum. Because both of them are greater than 0. That's what the condition says, minimum. So the last thing is, after you find the nature of the point, let's say you're getting a maximum point or the minimum point, after you conclude that the point is a maximum or minimum point, it is very much required to know what is the maximum value or the minimum value at that particular point. So which can be easily obtained by just substituting the given question, given the obtained minimum point in the given question. So in the place of x 2 by 3 and y minus 4 by 3, we can substitute in the given original function in the given question. That is the minimum point, the minimum value will be, it will be in the given function, we just need to substitute the critical point 2 by 3 comma minus 4 by 3. Okay. So when I substitute the minimum point in the given question, then the value might be around minus 4 by 27. So this is the required minimum value. Okay. Thank you.